Let's talk about the skeletal system. The skeletal system is probably one of the more familiar organ systems to people outside of bio. We've all seen a picture or a model of a skeleton. Maybe we've broken a bone and seen an x-ray. Maybe we know the names of a couple of bones. But there's more than meets the eye to the skeleton. Now, if you're looking for a video about the anatomy of the skeletal system, about how to name humerus, radius, ulna, carpals, metacarpals, phalanges, etc., there are people with great softwares out there that can show you like a 3D looking skeleton and turn it around and show you all the bones and bone markings in great detail. I don't have that, so I'm going to use this video to talk about what's, in my opinion, the harder stuff, like the microscopic anatomy of bone and the physiology of how bone works. So I'm going to start by talking about the classifications of bones because this relates to how they're structured on a smaller level. So there are long bones. Long bone is probably what you would draw if somebody asked you to draw a bone. It's what a dog bone kind of looks like. This is like the bones of your arms and legs, like the humerus or the femur or the radius. Those are examples of long bones. Anything that has like that classic bone shape. Short bones are basically, they're more square than long bones, so they're about as long as they are wide. Examples of this would be like the carpals, which are the bones of the wrist, or the tarsals, which are the bones of the ankle. Then we have flat bones. Flat bones are kind of what they sound like. These names are fairly logical, but they're not always going to be completely flat. So for example, the bones of your head, of your skull, like the parietal bone and the frontal bone, those are examples of flat bones. The ribs are examples of flat bones. That one's kind of shocking, but they are. The sternum, which is that bone in the middle of your chest here, that's a flat bone. And then there are irregular bones, and irregular bones basically don't fit any of the classifications that I just talked about. So an example of an irregular bone would be like the sphenoid bone in the skull, which looks like a butterfly, or the vertebrae, or your hip bones are irregular bones. And then there's one more type of bone that actually falls underneath the umbrella of short bones, and these are sesamoid bones. They're called sesamoid because they look like sesame seeds, and they are little bones that go along the tendons of some muscles. The only sesamoid bone that's really probably relevant to you is the patella or the kneecap, and that sits along a bunch of different tendons and ligaments, and yeah, that's the only sesamoid bone that you probably care about. Some people will mispronounce it sesamoid bone. That does not help because sesamoid will tell you the shape of it. So because the long bone is kind of the classic bone, I'm going to go over the anatomy of the long bone first on a more detailed level. So we have different regions of this bone. The ends are called the epiphyses. So epi means on top. And there's one on the bottom too, but they're at the ends. Those like rounded out parts, they are called epiphysis, singular, epiphyses, plural. This long part, the shaft of the bone, is called the diaphysis. Dia means through, so the diaphysis goes through the bone. And then the regions between the epiphysis and the diaphysis, they are called metaphyses. So one of them is a metaphysis. And meta means like in the middle. So hopefully these names are pretty intuitive to you. The epiphyses are made of what's called spongy or cancellous bone. So we can see the anatomy of that up closer if we zoom in, and this is the one that actually looks like a sponge. So hopefully that name also makes sense. The little pieces of bone that are woven through there, they're called trabeculae. And then this bone that surrounds the whole thing is called compact bone. So the diaphysis on the outside and part of the epiphysis on the outside is made of compact bone. And compact bone kind of has this structure with these tree trunk looking rings. And if you've learned about tissues, you've probably seen that bone connective tissue looks like a tree trunk. So the compact bone surrounds the bone except for at the ends where the joints are, and that is instead surrounded by what's called articular or joint cartilage. Inside the diaphysis, we have a cavity. It's called the medullary cavity. That's where the bone marrow goes. Now, when you're a kid, all of your bone marrow is going to be what's called a red bone marrow. This contains cells that are called hematopoietic stem cells. That means that when they grow up, these stem cells are going to be blood cells. As you age into adulthood, a lot of your red bone marrow on your limbs is going to turn into yellow bone marrow, which is more like fat storage. But red bone marrow will remain in some other bones. And that's the anatomy of the bone, but believe it or not, it gets more complicated later on. But we'll table that for now because we're going to look at the anatomy of a flat bone. So in flat bones, we don't have a medullary cavity. We just have like a sandwich. And in this sandwich, the bread or the outside of the sandwich is compact bone, and then the meat of the sandwich, the inside, is spongy bone, and the spongy bone on the inside of a flat bone is called the diploe. So now for the more complicated stuff. We have all this crazy anatomy inside of compact and spongy bone, but in order to understand how that works, we have to understand the cells that live in bone. And often we forget that bone is alive, but bone is alive, and we have different cell types that make up bone. So one cell type is called osteoprogenitor cell, and if you know the word progenitor, it means that it's before something else. It's going to turn into something else. So the osteoprogenitor cells are stem cells, and their job is basically to grow up into an osteoblast. Osteoblasts are going to be cells that build up bone matrix. Bone is a type of connective tissue, and whenever you have a connective tissue, you have cells, and then you also have what's called ground substance or matrix, and that's like all around the cells is non-cellular material that supports the tissue. In some connective tissues like blood, it's really fluid, but in other connective tissues like bone, it gets really hard. And the matrix that osteoblasts secrete has two parts. So bone matrix has osteoid and it has hydroxyapatite. The osteoid is the organic part of it. Organic means that it has carbon bound to hydrogen. So the osteoid is going to be made of things like proteoglycans and glycoproteins, and a large part of it is type 1 collagen. Collagen is a connective tissue protein, and it's really, really abundant. I think it's the most abundant protein in your body, and its job is to resist stretch. So if you stretch out the bone, then the bone will be kind of absorbing that shock because of collagen. And then the hydroxyapatite, that's the inorganic part of bone. That's going to be the hard stuff. That's going to be what makes bone not pliable. So hydroxyapatite is going to be made of calcium. That's why we need calcium for our bones. It's also going to be made of phosphate and hydroxide and some other stuff like magnesium and sodium and fluoride also. I love this picture. It is showing you what happens if you don't have either component, if you don't have osteoid or if you don't have hydroxyapatite. And I've actually had students come to me with experiments, especially during COVID when they couldn't come in person. They would come with an experiment where you put one bone in vinegar and you put one bone into, you cook it. So when you cook it, you're going to denature the protein, you denature the collagen, and what happens is the bone gets really brittle because you don't have the resistance to stretch anymore, so it'll just break into lots of pieces. If, on the other hand, you put it in vinegar, vinegar's got acid in it. It's going to make the different ionic components of the hydroxyapatite dissolve and go away, so the bone will stay together, it won't be brittle, but it'll be really elastic because you're losing the hard part and you kind of only have the osteoid remaining. So that's the role of the different kinds of bone matrix, and osteoblasts, their job is to make the bone matrix. So they will take the components of the osteoid and the components of hydroxyapatite and kind of put them together. And when they do that, the bone around them is going to get harder because of the hydroxyapatite. And eventually it's going to solidify, or what we call ossify. So when the bone ossifies around this osteoblast, it's going to trap itself in. It can't move away if the bone around it is hard. It's going to make a little home for itself, and that home is called a lacuna. And it's going to mature into what we call an osteocyte. Whenever you hear cyte at the end of the word, it means cell. Blast meant that it was going to grow into something else. When you hear the word progenitor, that means it's at the really beginning of its growing up, its differentiation as a cell. When you hear blast, it's like almost there, but something blast means it's still going to turn into a different cell type. But osteocytes, they are all grown up. They're going to sit in their lacunae and they're going to communicate with each other, and we'll see more of that later. But basically, they're done secreting bone matrix. The osteoblasts are going to be the more important ones. We're going to talk more about them later. There are also osteoclasts. Osteoclasts are these guys. So osteoclasts are derived from a similar cell that makes macrophages. And if you've learned about the immune system, you know that these cells, they eat stuff. Macrophage means big eater. So osteoclasts form from the fusion of lots of these cells. So they're going to be multinucleated, and they kind of look like these gooey little demon monsters in the pictures that my textbook has. And their job is to do what's called bone resorption. And resorption of bone means they take all that stuff that the osteoblast built and they undo it. And they put that stuff back, usually into the bloodstream. And that will become important also later. So being armed with the knowledge of these cells, osteoprogenitor cell, osteoblast, osteocyte, osteoclast, we can now look at the microscopic anatomy of bone in even more detail. So the kind of unit of bone is called an osteon. Some people call it a Haversian system. In general, in anatomy and physiology, we're trying to move away from what we call eponymous terms, or things that are named after people. But a lot of teachers grew up and learned their stuff before that, so you might hear it being called a Haversian system, but it is also called an osteon. So osteons have these concentric rings called lamellae, and within the lamellae are lacunae. I know it's very confusing, but we have to learn to differentiate these terms. So the lamellae are the rings that look like the rings on a tree trunk. The lacunae are the little places where the osteocytes live. So this is an osteocyte, and if we zoom in on it, here's the osteocyte, and it's really hard to see the lacuna. The lacuna is basically, if we took the osteocyte out of this, it would be the space that the osteocyte lives in. And the osteocyte is going to send out these projections called canaliculi. Because remember, the bone matrix is hard, but this osteocyte is still living. It needs to get nutrients. So it's going to send out these canaliculi to communicate with other cells and to receive nutrients from this central or Haversian canal. And in this canal, we have blood vessels, and we also have nerves, because yes, bone is innervated. And then we have collagen fibers on the outside of these osteons, and the collagen fibers are going to go in opposite directions. They're going to go perpendicular to each other. And the reason for that is, again, to give the bone a little bit of elasticity and stretch or compression resistance. So this is what it looks like in a bigger picture. Remember that on the bone we had compact bone and then spongy bone. That's what's going on here. And we have osteons with their lamellae, and then we also have what's called circumferential lamellae, because if you put a bunch of circles in, you're not going to make the right shape for a bone. So we have circumferential lamellae on the outside, and then we have internal circumferential lamellae on the inside, and we have interstitial lamellae, which are these little pieces in here. Those guys are not so important to know as the structure of the osteon. This is really the important thing to know in terms of microscopic bone structure. And then for spongy bone, remember we have these trabeculae. Trabeculae do not have central canals. However, they do have osteocytes. They do have lacunae, because that's where the osteocytes live. And they do have canaliculi, which remember are those projections that the osteocytes send out. And they do have lamellae, which are the concentric rings. So the lamellae here are kind of squashed into a weird shape, but they're still lamellae. And then we don't have the canal with the blood vessels, so How the heck do the osteocytes get their nutrients and deposit their wastes? Well, they're going to do so by diffusion into the spaces here around the trabeculae. So that's what bone looks like. We can also discuss how bone grows, because when you have an embryo, bone is not going to be there initially. It's going to have to come from stem cells. So it comes from what's called mesenchyme. And there's two ways how bone grows. I'm going to first talk about how flat bones grow. So flat bones are anything that kind of looks like a flat bone. I'm going to talk about flat and long, but anything that more resembles a flat bone, like maybe short bones, I think also go through this, is called intramembranous ossification. That's the way that they're made. So in this way, we have osteoprogenitor cells that kind of just collect themselves in a certain area, and they're going to work from the outside in to make osteocytes. And the bone that first forms is going to be called woven bone, and then it's going to be replaced with lamellar bone, because remember the lamellae? And again, we have this anatomy of the flat bone with our outsides that are made of compact bone and our inside diploe that is made of spongy bone. So this is, for example, the skull, as you can see in the top left. And then we have this other way. This is called endochondral ossification. Chondro means cartilage. The only exception I can think of is mitochondria, which are not made of cartilage. But endochondral ossification tells us that the skeleton of the fetus is going to be mostly made of cartilage at first. So here's a little fetus, and its bones are not bone yet, they're all cartilage. And eventually that cartilage is going to be replaced by bone. And it's going to make a lot of sense because cartilage and bone have similar systems. Cartilage cells, or chondrocytes, they also live in lacunae. And because cartilage doesn't have any blood supply, basically what's going to happen is these chondrocytes are going to die. And they're going to leave their lacunae as spaces. And those spaces are going to be inhabited by osteoblasts that become osteocytes. They're kind of going to migrate inward and take up those spaces. And then we start getting bone in this fetal skeleton. And once this becomes a person, once they're born, then we have this system where the bone can keep growing in these epiphyseal plates. So remember that the end of the bone is called the epiphysis. Well, the epiphyseal plates are these little regions in the epiphyses that are made not of bone, but of cartilage. And this is where the growth occurs, so they're also called growth plates. The rest of the bone is going to be bone, but the growth plates are going to be cartilage. And if you kind of zoom in on the growth plate or the epiphyseal plate, you can see the way that the cells migrate through and how they slowly turn from growing cartilage, from resting cartilage to growing cartilage to bone cells eventually. And that's how the bone is going to grow from these epiphyseal plates. And eventually they will close up, there will be no more epiphyseal plate, and they will become an epiphyseal line. So if somebody dies and you look at their bone and you can see where the epiphyseal line is or how much of an epiphyseal plate that they have, you can tell their age at death, which is, I think, very interesting. So now we can look at what's called bone remodeling, because even when your bones are done growing, they're still very dynamic structures. Bone remodeling has to do with what we talked about earlier. A couple major players, we have osteoblasts, and these are going to build bone. Blasts build bone. Osteoclasts are going to do what we call resorbing bone. One mnemonic that I've heard people use is osteoblasts build bone, osteoclasts claw at bone. So this is how they work. They work antagonistically. They work against each other. And different hormones in our bodies and different conditions that we have are going to influence which one is working more than the other and what the net or overall effect is on our bones. So one set of hormones is parathyroid hormone and calcitonin. So parathyroid hormone is way more important. Parathyroid hormone. And parathyroid hormone is made in the parathyroid glands. So we have a thyroid in our neck that kind of looks like a butterfly, and the parathyroid glands are these really little, like kind of smaller than a fingernail, little glands, and they produce parathyroid hormone. Parathyroid hormone is influenced by the levels of blood calcium, and the really important thing to understand in this is that calcium is either going to be in the bone or the blood. If we are making more hydroxyapatite, more bone matrix that has osteoid and hydroxyapatite, we're going to take calcium from our blood to make that hydroxyapatite. If we are resorbing bone, we will kind of destroy or break down that hydroxyapatite, and the calcium from that, along with probably other stuff in it, is going to go into the blood. So higher blood calcium probably means less bone density, and lower blood calcium probably means higher bone density. And this is how we end up regulating our calcium. Calcium regulation is also really important for the function of nerve cells and muscle cells. Calcium triggers muscle contraction. It gets stored in what's called the sarcoplasmic reticulum in muscle cells, and it triggers our muscles to contract. So basically what I'm trying to say is blood calcium levels are important and bone calcium levels are important, and calcium is going to be in one or the other. And of course there's other ions like phosphate, etc., but calcium is the one that's going to trigger parathyroid hormone. This works by a negative feedback mechanism. So basically, if calcium gets too low, this is going to trigger parathyroid hormone, and parathyroid hormone is going to raise blood calcium levels. So this is going to involve taking calcium from the bone and putting it in the blood. So which of these two cells do you think is going to be more activated by parathyroid hormone? The osteoclast, right? And if you've already learned about this and you're saying, no, it's the osteoblast that gets regulated and activated, and then it tells the osteoclast, you're technically right. But for the sake of simplicity, we're going to say that parathyroid hormone is going to activate the osteoclast. It's going to increase osteoclast activity and thus take calcium out of the bone into the blood. So we would also expect osteoblast activity to be suppressed. So the antagonistic hormone that goes against parathyroid hormone is called calcitonin. Parathyroid hormone has a lot more influence on blood calcium than calcitonin. So we don't really care that much about calcitonin, but when it comes to these two hormones, because they're the opposite of each other, they're often going to be like two different answer choices. Or you may get asked about calcitonin, even though it's not so important in like the actual application of this stuff to real life situations. But if you have too much calcium, this is going to trigger calcitonin. So these calcium levels, remember, are in the blood and not in the bone, and that's an important thing not to get confused on. These hormones are triggered by calcium in the blood. So if you have too much calcium in the blood, calcitonin is going to lower blood calcium levels. And it's going to do this by doing what to osteoblast and osteoclast? It is going to suppress the activity of osteoclasts, so less calcium gets resorbed. And it's going to raise the activity of osteoblast because the osteoblasts are going to build up bone, so they're going to take that calcium out of the blood, take the excess calcium, and build more bone. So I hope these two make sense. The other influencer of blood calcium and bone remodeling is vitamin D. And you've probably heard that if you go out and get some sun, you'll get vitamin D. Misconception might be that the sun just doesn't give you vitamin D. You have to already have the inactive form. The sun just provides the energy to catalyze it to become the next form of itself in the series to get it activated. So this process is going to start in your skin, right? So we are going to have a predecessor, and this is called 7-dehydrocholesterol. 7-dehydrocholesterol is going to get triggered by sunlight to make this other molecule, and this is called cholecalciferol. Cholecalciferol is going to travel in the blood, and it's going to go over to the liver, and the liver is going to turn it into calcidiol. Calcidiol is going to travel to the kidneys, and it's going to turn to calcitriol. Now, the interesting thing is that parathyroid hormone, which remember is supposed to raise blood calcium when it's too low, is going to activate this process. And we'll see why in a minute. So calcitriol is the activated form of vitamin D. And calcitriol is going to do a couple different things. Calcitriol is going to increase absorption. I'm going to write this over here where I said vitamin D. Increase absorption of calcium in the intestine. So when you eat something with calcium, if you have vitamin D activated, more calcium is going to get absorbed. This is not the same as resorb out of the bone. This is absorb from the intestine. You are also going to increase reabsorption, which is, again, a different thing. I know, very confusing. Of calcium in the kidney. So it gets activated in the kidney, but then it goes and tells the kidney to reabsorb more calcium. The kidney is going to turn blood into urine. It's going to filter the blood. But reabsorption is where it goes, okay, wait, before you go out of the body, we need all these things back. And vitamin D says one of those things should be calcium. Vitamin D is also going to increase osteoblast activity, osteoclast activity. But because it does so much absorbing and reabsorbing of calcium, we consider the net effect to be building up bone calcium and building up blood calcium. So it's going to do everything. And that is how bone is regulated. So all you have to remember is that these things work on the negative feedback system. So if blood calcium is too high, we're going to try to lower it. If blood calcium is too low, we are going to try to raise it. So this figure summarizes that stuff nicely. And that is basically it. That is how bones work. I think they are super interesting and very fun. And I hope this made everything make a little bit more sense.